Hey everyone, let's just jump right in. Welcome to The Explainer. Today, we're taking a look at something you use literally every single day, probably without giving it a second thought, and that is language. But we're not going to look at it the way a poet or a novelist would. Nope, we're putting on our math hats today. Because underneath the surface of all the words we speak and write, there's actually a hidden, incredibly precise algebraic structure. Seriously, you're performing complex algebra every single time you order a coffee or shoot off a text.
Take a look at this. This villa costs a fortune. This is a completely everyday, deceptively simple sentence we pulled straight from today's source material. You read it left to right, you know exactly what it means, and you move on, right? But there is actually a huge amount of computational work happening behind the scenes to make this simple sequence of words function.
So I want you to think about this for a second. What is the hidden mathematical code inside this sentence? I want you to try and look past the literal meaning, the really expensive house, and consider the invisible rules governing how these exact words are allowed to snap together. There's a rigorous architecture here, and your brain just processes it instantly.
All right, part one, more than meets the eye.
Let's peel back the very first layer here. We've got to break down a pretty fundamental misconception about how sentences are actually built. And I'm going to challenge your basic assumptions right out of the gate with a super simple question. How many words are in the sentence we're about to look at?
Here's our example. The dog sees the cat eat the mouse. Now, if you're just counting dictionary vocabulary, the word the is just one single word, right? But look at how it appears 3 distinct times. This tells us something absolutely crucial. A sentence isn't just a handful of magnetic poetry tiles tossed randomly onto a fridge. It's a highly organized filing system. It's not just about the words themselves, it's about exactly where those words live. The word the has 3 distinct, strictly ordered positions.
So the key takeaway here is we have to stop talking just about words and start talking about occurrences. An occurrence is a specific position in a sentence. And these occurrences, they're governed by strict mathematical postulates. Now, don't let terms like irreflexivity or transitivity freak you out. Just think of occurrences like people standing in line at the grocery store. Irreflexivity just means you can't physically stand in line behind yourself. It's physically impossible. And transitivity simply means if person A is in front of person B and person B is in front of person C, well, person A is obviously in front of person C. These occurrences lock into place on a linear timeline, and they never, ever overlap.
Moving on to section 2, finding the building blocks.
Okay, so now that we know we're dealing with strictly ordered occurrences, let's see how these individual pieces actually start grouping together to build a structure. Enter the concept of the constituent. If individual words are like single bricks, constituents are the prefab walls of our sentence construction site. A constituent is a sequence of words that acts as a single, unified structural block. And the way we prove a sequence is a constituent, we see if it can be swapped out or replaced by a single word. If it can, boom, we know those specific words are glued together mathematically. Let's actually walk through this substitution test step by step so you can see how it works. First, in our original sentence, we identify a sequence we want to test out. Let's grab a fortune. Next, we try to replace that entire sequence with the single word much. And finally, we look at the result. This villa costs much. Now, okay, it might sound a tiny bit clunky, but because the sentence still totally works grammatically, we've mathematically proven our case. The grammar engine inside our head accepts it. That means a fortune operates as a distinct, unified block. It's a constituent.
But here's where it gets kind of wild. What if we took "this villa costs a fortune" and completely replaced the massive constituent "villa costs a fortune" with just a single action word, like runs? We get "this runs." We literally just swapped out a massive, expensive house and its price tag for a tiny action, and this brilliantly highlights a real mind-bending linguistic plot twist. Meaning versus grammaticality. "This runs" completely destroys the original meaning of our sentence, right? We're definitely not talking about real estate anymore. But it is still a grammatically flawless English sentence. These deep structural rules only care about preserving grammaticality, not logical meaning. The math of language is totally blind to what you're actually trying to say. It just cares that the algebra balances out. It's a huge aha moment about the magic of the human brain. We naturally separate meaning from structure without even trying.
Now, to map these blocks out accurately, we follow what are basically the inviolable laws of physics for our sentence universe. Rule number 1, constituents are continuous. There's no jumping over other words. Rule 2, they are non-crossing. Think of this visually. If two constituents share a word, one has to be completely swallowed inside the other. You can't have half a block sticking out of another block. And rule 3, every single occurrence of a word forms its very own base-level constituent.
Let's look at Section 3, Mapping the Sentence Tree.
So we've successfully identified the blocks. Let's actually draw the architectural blueprint of how they stack up. By grouping our constituents, we can visualize the sentence using mathematical brackets. Look at how they slowly nest inside one another here. A and fortune fare up first, then cost swallows a fortune. Meanwhile, way over on the left, this and villa pair up. And finally, those massive outer brackets swallow the entire thing. It literally looks exactly like computer code, doesn't it?
If you take those nested brackets we just looked at and pull them apart vertically, kind of like pulling apart an accordion, you get a tree. A tree is a hierarchical structure that maps these constituents to points called nodes. And because of that strict non-crossing law of physics we talked about earlier, every single branch neatly connects upwards, continually narrowing down until it hits a single ultimate point called the root node. And the reason this matters is because that single root node proves that the entire sequence is one unified, cohesive thought.
Now, every single node on that tree belongs to a specific substitution class, or category. Let's check out the table here. This villa belongs to the category DP, or determiner phrase. Put simply, a DP just points to the specific thing we're talking about. Costs of fortune is a VP, or verb phrase. This contains the action that the thing is doing. And that ultimate root node at the very top, the finish line, that's category S, which stands for sentence. If a sequence of words combines properly and meets all the mathematical requirements to hit that S node at the top, congratulations, you've spoken a valid sentence.
All right, Section 4, the context-free grammar engine.
Time to zoom all the way out. We've gone from words to occurrences to constituents to trees. And this brings us to context-free rules. These are the literal, macro-level algebraic equations, the master blueprint that your brain follows. Let's walk through them. That arrow symbol, it simply means can be rewritten as. So S can be rewritten as a DP and a VP. A DP can be rewritten as a D and an NP. A VP can be rewritten as a V and a DP. And eventually those abstract categories turn into actual terminal words, like the verb turning into costs. And here's the kicker. It doesn't matter what the surrounding context is. These mathematical rules apply every single time.
Let's actually treat this like we're watching a machine come to life on a factory floor. In real time, we start the engine at step 1 with a single abstract symbol, S. In step 2, the rule forces S to split into DP and VP. In step 3, the rules force those to split even further down into D, NP, V, and DP. Finally, in step 4, those abstract symbols are replaced by the dictionary words, "This villa costs a fortune." The grammar engine has mathematically generated our sentence right out of thin air. We started with a single letter, and the algebra cascaded down to create English.
And that right there is exactly what a context-free grammar is. It's a set of terminal symbols, which are our actual dictionary words, and non-terminal symbols, like S and VP, paired with rewrite rules. Because you can loop these rules over and over, this simple machine can generate a literally infinite number of grammatical sentences. And here's a pretty surprising fact for you. This exact same concept, context-free grammar, is what computer scientists use to build programming languages like Python or C++. It is the perfect bridge between human language and machines. It's the ultimate language-generating engine. Which leaves us with this final, honestly awe-inspiring thought from our source material today. If a handful of context-free rules can generate infinite strings of sentences, how incredibly hard would it be to write a master set of rules that generates only proper English and never makes a grammatical mistake? Linguists and computer scientists have spent decades trying to map the complete mathematical grammar of English, and it is overwhelmingly complex. Yet, your brain, that incredible biological machine sitting inside your head right now, runs this entire context-free grammar engine flawlessly, in milliseconds, every single time you open your mouth to speak. Thanks so much for joining me on this explainer, and the next time you hear a simple sentence, I really hope you see the hidden math holding it all together. Catch you next time.